General relativity, step by step. Last time I showed that we can use a gauge transformation to require that this condition here holds. We can always find a gauge transformation that makes this equation here true. And if that's the case, as I showed in screencast number 14, which I'm going to show you again. No, that was number 15. Let's try again. 14. General relativity. Yeah. Shut him up. Right to the end here. All these three terms here vanish. 1, 2, 3, they just disappear. And we're left with this one here, which I'm going to write out. I like it so much, I'm going to write it out again. Di mu, h bar equals 0. Oh no, it was equal to, was it 8 pi or 16 pi? It was 16 pi, wasn't it? Let me write it out again. Let's just kill that. Okay. We are left with di mu upstairs of h bar mu nu. Oh, actually, I've got the mu written twice. Let's change that mu to an alpha equals minus 16 pi Newton's law of gravity times stress energy tensor. What's free? It's mu and nu on the top. Okay, we've seen this operator quite a lot. Di alpha. Of course, it's summed over alpha. Let me rephrase what that comes out to be. That turns out to be di alpha eta alpha beta di beta. That's the same thing. That's the same operator. You see, I've got it's contracted over alpha and it's contracted over beta as well. You see, it's just the same thing. Well, that, and eta, of course, I'm only working to first order, is equal to minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So this operator comes out to be minus di t for this term here, minus because it's a minus 1, plus di x, which is that term there, di y, plus di z. That's what that operator turns into. Oh no, the bracket's in the wrong place. There. Equals minus di 2 di t squared plus di 2 di x squared. I've got the minus di 2 di y squared, di 2 di z squared, acting on h bar mu nu. H bar mu nu equals minus 16 pi gravitational constant g mu nu. T for tensor mu nu. Equals 0 in a vacuum. I'm not going to talk about the waves in anything other than a vacuum, so I'm just going to set it equal to 0. But if you really wanted to, we could put non-zero terms in there. Well, actually, I will sort of put stress energy tensor because I'm going to talk about Weber bars later on, but we'll come back to that later. This operator here, which I've just been casually calling di alpha, is sometimes called quad. By analogy with this symbol here, or quad squared or quad. Yeah, different people use different things. We've got the differential operator del. So we can write this whole thing down here as quad h bar mu nu equals 0 for a vacuum, or minus 16 pi, whatever. Or I can rewrite it in a slightly different form. Di 2 di x squared plus Laplacian. I think is it Laplacian that with a squared? I can't remember. H bar mu nu equals 0. So again, we've got our operator acting on this thing here equals 0. This is a wave equation, of course. Wave equation. Haha. Isn't that wonderful? So finally, after, what is it, 21 screencasts? Something like that. We've got the Einstein field equations and simplified the living daylights out of them by linearizing, and also by now having a gauge transformation that allows us to simplify our equations. And now we've got something we recognize. we have got a wave equation. I'm going to solve that. We need an extra, we haven't exhausted all our gauge freedom yet. We've just insisted that the, where are we? That, where was it? We wanted this to be true. We've used this gauge freedom here, but we do still have sufficient coordinate freedom to simplify our equations down a little bit more. And I'm going to do that in subsequent screencasts. But for the moment, I want you to see we have a wave equation in terms of this fictitious tensor h bar, which equals 0, under the assumption that h bar mu comma nu equals 0, which is our sometimes called the Lorentz gauge, or the Lorentz condition. Beautiful. I'm going to stop there. Stop.